Hey everyone, welcome back. Before we jump into today's absolutely mind-bending topic, I'm sending out huge virtual hugs and the very best wishes to every single one of you watching. Seriously, wherever you are in the world, I truly hope you're feeling fantastic, taking excellent care of yourselves, and staying healthy. That's the most important thing, always. Now, get ready to have your perception of time and our planet completely shaken up, because we're talking about something that sounds like pure science fiction but is 100% real science. Earthquakes can actually make our days shorter. Yep, you heard that right. When a massive earthquake rips through the Earth's crust, the sheer power of that event can literally speed up the planet's rotation, shaving tiny fractions of a second off the length of a day. It sounds impossible, right? How can ground shaking change how fast the whole Earth spins? Well, buckle up, because it all comes down to a fundamental principle of physics involving mass, rotation, and the delicate balance of our entire planet. It's one of the most incredible hidden consequences of these powerful natural events. So, how does this work? Think of the Earth like a giant spinning top, or even better, like an ice skater performing a spin. You've probably seen how a skater starts a spin with their arms spread wide, spinning relatively slowly. Then, when they pull their arms tightly in towards their body, they suddenly spin much faster. That's because they've changed their moment of inertia. Basically, they've concentrated their mass closer to their center of rotation. When mass is pulled in closer to the axis of spin, the object spins faster to conserve its angular momentum, which is the physics term for the quantity of rotation it has. The Earth operates on this exact same principle, but on a planetary scale. Our planet spins on its axis once roughly every 24 hours, giving us day and night. This spin, this angular momentum, is a constant value. It doesn't just disappear. But how fast it spins depends on how that mass is distributed relative to the spin axis, which runs from the North Pole to the South Pole. Now, enter a truly massive earthquake, particularly the kind involving what's called a thrust fault. This happens when one massive slab of the Earth's crust is forced upwards and over another slab during the quake. Imagine two gigantic tectonic plates colliding. One plate gets shoved underneath, forcing the other plate to buckle and lift upwards. This violent movement doesn't just happen horizontally, it also shifts vast amounts of rock vertically. And here's the crucial point: when this upward thrust occurs near the equator, it moves significant amounts of the planet's mass slightly closer to the Earth's spin axis. Think of it like the skater pulling their arms inwards. Mass that was once spread a bit farther out, like rock slightly bulging at the equator, gets shifted upwards and therefore slightly inwards towards the planet's center of rotation. It's a minuscule shift on a human scale, maybe just a few centimeters or meters, but when you're talking about moving mountains worth of rock across hundreds of kilometers, the cumulative effect on the planet's mass distribution is real and measurable. This inward shift of mass reduces the Earth's moment of inertia, its resistance to changes in rotation. Since the total angular momentum of the spinning Earth must stay constant, thanks to the conservation laws of physics, the only way to balance out this reduction in moment of inertia is for the planet to spin a little bit faster. And spinning faster means the time it takes to complete one full rotation, one day, gets very slightly shorter. It's the exact same reason the ice skater spins faster when they pull their arms in. The Earth, in effect, pulls some of its mass slightly in during these colossal quakes, so it spins a tiny bit faster to keep its overall rotational momentum the same. It's a breathtakingly elegant demonstration of fundamental physics playing out on the grandest possible stage. You might be thinking, okay, but how much shorter are we talking? A second? A minute? The effect, while real and scientifically significant, is incredibly tiny from our human perspective. We're talking about shortening the day by microseconds, that's millionths of a second. For example, the monstrous magnitude 9.1 earthquake that struck off the coast of Sumatra in 2004, triggering the devastating Indian Ocean tsunami, is estimated to have shortened the length of a day by about 6.8 microseconds. The massive magnitude 9.0 earthquake that hit Japan in 2011 shortened the day by roughly 1.8 microseconds. Even the powerful magnitude 8.8 quake in Chile in 2010 shortened the day by an estimated 1.26 microseconds. These numbers seem vanishingly small, almost laughably insignificant in the context of our daily lives. You'd never notice it on your watch or phone. But for scientists meticulously tracking the precise rotation of our planet, these changes are detectable and meaningful. So, how do scientists even measure such incredibly tiny changes in the length of a day? They don't use ordinary clocks. They rely on incredibly precise technology. One key method uses GPS satellites. These satellites constantly send signals down to a global network of ground stations. By very precisely measuring the distance between these satellites and the ground stations over time, scientists can detect minuscule changes in the Earth's rotation and the positions of the continents themselves. Another crucial tool is called Very Long Baseline Interferometry, VLBI. This involves using networks of radio telescopes scattered across the globe to observe distant quasars, incredibly bright objects billions of light-years away. Because these quasars are so incredibly far away, they act like fixed points in the sky. By very carefully timing the arrival of the quasar's radio waves at different telescopes on Earth, scientists can measure the orientation of our planet in space and the speed of its rotation with mind-boggling accuracy. It's like using the universe itself as a giant, ultra-precise gyroscope. Additionally, scientists use data from laser beams bounced off reflectors left on the Moon by Apollo astronauts, lunar laser ranging, and sophisticated models of the Earth's structure and gravitational field. Combining all this data allows them to detect rotational speed changes down to the microsecond level and pinpoint how events like massive earthquakes cause these shifts. It's important to note that not every earthquake has this effect. To measurably change the Earth's rotation, an earthquake needs to be truly enormous, typically magnitude 8.5 or higher. Smaller quakes simply don't move enough mass over a large enough area to make a detectable difference. The type of fault movement also matters significantly. Thrust faults, where one slab of crust is shoved up and over another, are particularly effective at shifting mass vertically and radially inwards. Strike-slip earthquakes, like the San Andreas Fault where plates slide past each other horizontally, cause massive destruction but generally don't shift mass vertically in a way that significantly changes the moment of inertia. The location also plays a role. Earthquakes happening near the equator have the biggest potential impact because that's where the rotational velocity is highest, and shifting mass there has the greatest leverage on the planet's spin. Moving mass near the poles has much less effect. So, it takes the perfect storm, a truly gigantic quake, involving a major vertical thrust component, ideally near the equator, to noticeably nudge the planet's rotation speed. The shortening of the day isn't permanent in the sense that it's a one-way trip. The Earth's rotation is constantly being influenced by a whole orchestra of factors. The gravitational pull of the Moon and Sun causes tides not just in the oceans, but also in the solid Earth itself and even in the atmosphere. This tidal friction acts as a constant, very gentle brake, slowing the Earth's rotation down over extremely long timescales, making days get longer by about 1.7 milliseconds per century. Changes in atmospheric winds, ocean currents, the movement of water between ice sheets and oceans, like melting glaciers, and even the shifting of the Earth's molten outer core all contribute tiny, ongoing fluctuations in the planet's rotation speed. A massive earthquake is like a sudden, sharp jerk in this system, a temporary perturbation. While the mass shift caused by the quake itself is essentially permanent, the rock stays where it moved. The overall rotational speed continues to be influenced by all these other factors. So, the day might be a few microseconds shorter after a megaquake, but the long-term trend of very gradual slowing due to tidal friction continues. The earthquake effect is a significant blip on a very complex graph of the Earth's rotational behavior. Understanding this phenomenon gives us a profound perspective on the dynamic nature of our planet. We often think of Earth as this solid, unchanging ball, but it's far from static. It's a complex, dynamic system where colossal forces are constantly at play beneath our feet. A single event, lasting just minutes, can literally alter the spin of the entire planet. It highlights the incredible interconnectedness of Earth's systems, geology, the shifting plates, physics, angular momentum, and even timekeeping. It shows us that even events we experience as purely destructive and localized have subtle, global consequences that ripple through the fundamental properties of our world. It's a humbling reminder of the sheer scale of energy released in these events. The energy that can shift enough rock to change the planet's rotation is almost incomprehensible. It also showcases the astonishing precision of modern science. The fact that we can measure a change of a few microseconds in the length of a day, caused by an event thousands of miles away, is a testament to human ingenuity and our ability to understand the intricate workings of our cosmic home. So, the next time you hear about a devastating earthquake somewhere in the world, remember this incredible hidden consequence. Beyond the immediate human tragedy and landscape changes, that event sent a ripple through the very fabric of Earth's rotation. It literally made the planet spin a tiny bit faster, shortening our day by an imperceptible, yet scientifically profound, fraction of a second. It's a stark reminder of the awesome power contained within our planet and the delicate balance that governs its motion through space. It connects the violent shifting of the ground beneath us to the steady march of time itself. While we'll never feel those lost microseconds, knowing that such a connection exists deepens our appreciation for the dynamic, ever-changing, and utterly fascinating world we live on. It's a powerful example of how physics governs everything, from the spin of an ice skater to the rotation of a planet shaken by its own internal forces. Thanks for exploring this amazing piece of planetary science with me today. Stay curious, stay safe, and take care of yourselves.